Let's jump right into this explainer because today we're looking at something that literally keeps top AI researchers awake at night. We're talking about that terrifying widening gap between what AI can do and what we can actually control. We're witnessing this absolute explosion in AI capability, right? But our tools to manage it, they're seriously struggling to keep up. So today, we're not just going to admire the problem, we're exploring a massive structural shift in how we think about AI safety, drawn directly from some really cutting-edge source material. Okay, let's dive right into our roadmap for today. First up, the AI control problem. Second, we'll hit the capability first trap. Third, the energetic paradigm. Fourth, structural constraint before capability. And finally, a civilizational AI choice. Let's get to it. Section 1. The AI control problem. The widening gap between expansion and comprehension. So, look, we're seeing models with parameter counts scaling up into the trillions. Their reasoning depth isn't just about completing some simple single-step task anymore. They're doing multi-step reasoning, long-chain planning, even showing strategic behaviors. So I want to pose this structural tension directly to you. What actually happens when AI capability outpaces human control? Because this unpredictability we're seeing, it's not a glitch, it's not a bug, it's a natural mathematical result of increased capability complexity. The internal state space of the model is just expanding explosively. It's kind of like a game of chess. A beginner only sees, a few possible moves. But as you become a grandmaster, the number of possible moves and countermoves you calculate becomes absolutely massive. The combinations of possible AI behaviors are expanding exactly like that. But our human understanding of its decision pathways, it's just not expanding at the same rate. To see how the industry is handling this, let's look at two of the heaviest hitters in the AI space. On the left, we've got Anthropic. Their whole approach is alignment as internal correction. They use philosophical, constitutional principles to sort of correct outputs internally. Then over on the right, we have Scale AI. Their approach is evaluation as external constraint. They rely on super precise data, labeling, and these rigorous testing frameworks to constrain behavior from the outside. To use a quick analogy here, it's a bit like the difference between raising a child with strict internal morals versus putting them in a padded room with a giant rulebook. One relies on philosophical correction, while the other leans entirely on engineering precision. Which brings us to Section 2, the capability first trap, the illusion of difference. Now, what's really interesting here is that despite their completely different external narratives and engineering languages, the source material points out that both of these approaches actually share a massive foundational premise, and it's this. Capability must first exist, and only then is governance applied. This right here is the shared, unspoken assumption across the entire mainstream AI industry. The whole idea is that model scale and capability are the primary objectives, build the awesome capability first, and then safety, alignment, or data testing access this post-hoc compensatory layer. Basically, governance is treated as a meta-level adjustment that's only deployed after the AI has already formed its capabilities. But the framework suggests that as long as we follow this capability-first sequence, our governance is destined to be purely reactive. And that leads to three pretty terrifying consequences. First, rapidly rising governance costs. Every single time capability jumps, the cost to align and test it just spirals out of control. Second, patchwork reactive alignment. We are perpetually one step behind, fixing problems only after they pop up. And third, risk density gets compressed into latent spaces. Sure, we patch the visible risks, but the deep internal complexity just hides the danger in places we literally can't perceive. It is exactly like putting better, way more expensive seatbelts on a car that is accelerating exponentially. It's just fundamentally unsustainable. And that leads us to Section 3, the energetic paradigm, a shift in question. To solve this whole reactive trap, the research suggests we really need to stop asking how to make models more obedient after they generate an output. Instead, we need to ask a much more profound question. Which decision structures shouldn't even form in the first place? And this brings us to the energetic paradigm, or EP. EP is an architectural principle that builds stable intelligence through structural constraint, energy flow discipline, feedback control, and feasible state boundaries. I know, that's a mouthful, but in plain English, it means defining what actions are mathematically allowed to exist before the capability even expands. Think about our accelerating car metaphor from earlier. Instead of constantly designing better seatbelts for a runaway car, the energetic paradigm is about designing an engine that inherently, physically, cannot exceed safe operating temperatures. The absolute core takeaway here is this. Governance must be a generation condition, not an output correction. According to the text, EP establishes endogenous boundaries, meaning limits built from the inside out, based on physical sustainability and the low dissipation of energy. It literally prunes the state space before the AI even generates a response. If a decision pathway requires continuously increasing resources just to maintain stability, EP dictates that this pathway simply shouldn't be included in the feasible set of actions. The boundary comes from the system's own physical and energetic sustainability. It's not just some rule we slap on afterward. Let's move to Section 4, Structural Constraint Before Capability, the engineering reality. So let's see how this builds from high-level theory into actual, on-the-ground engineering reality. Because you might be wondering, how on earth do we take energy constraints and code them into a multi-billion parameter neural network? Well, at the engineering level, the source breaks this down into 3 concrete steps. Step 1, redefining the objective function. Mainstream models optimize purely for task success, right? But EP introduces an energy density penalty. In simple terms, the model is mathematically forced to find the most efficient, low dissipation, stable reasoning pathways, rather than just burning endless compute power to guess an answer. Step 2 is restricting the feasible state space through structural gating. If a pathway hits an energy or instability threshold, the system redirects it using feedback control. And Step 3, embedding governance into operation. Stability conditions are actually written into the core computational logic, so governance isn't some external review layer, it's an internal math condition that every single reasoning step has to satisfy in order to proceed. This table does a great job visualizing the core shift outlined in the research. On the left, we have mainstream output-oriented governance. This patches outputs within a given open space after generation. On the right, we have the generative redefinition of the energetic paradigm, which redefines the space itself before generation. Mainstream focuses on semantic compliance, what the model actually says. EP, on the other hand, focuses on structural constraint. What states are energetically permitted to exist at all? It's a complete topological shift. It fundamentally changes how the system's probability spaces are formed, actively restricting high-risk states from ever materializing. So why does this matter practically? Well, because these structural advantages completely flip the economics and the safety of AI. It treats constraint as the actual condition for safe capability generation. First off, governance costs flatten out instead of spiraling out of control. Why? Because the model's feasible state space is naturally pruned. You don't have to police an infinite space anymore. Second, you get stable, sustainable computational resource usage. No more violent fluctuations in compute power just to maintain a steady state. And third, and this is absolutely crucial, risk sources are eliminated, not just suppressed. Unsustainable pathways are cut right at the root, which means those latent risks never even have the opportunity to form. Which brings us to our final section, Section 5, a civilizational AI choice, the fork of the fourth revolution. Let's zoom all the way out for a second. The source frames this whole thing not just as a technical debate between engineers at Anthropic and Scale AI, but as a massive turning point in technological history. It's literally boundary engineering of capability generation logic. The crucial point is this: if artificial intelligence is truly the fourth scientific revolution, the fork in the road is not about whose model scale is larger. Think about it. Past scientific revolutions reshaped our understanding of mechanics and space-time by rewriting boundaries, while the current revolution is rewriting how decisions and capabilities are generated. The framework suggests the true fork we're facing is whether capability generation is embedded within and constrained by physical sustainability. Which leaves us with this final, incredibly important thought to consider. Will we allow AI capability to expand blindly, perpetually playing catch-up with reactive, increasingly expensive safety patches? Or will the industry demand a structural shift, utilizing the energetic paradigm to ensure AI operates only within physically sustainable, stable bounds? It's a choice that will quite literally dictate the stability of our technological civilization. Thank you so much for exploring this deeply fascinating explainer with me today.